So what are the crystal imperfection is point defect, line defect, surface defect, and volume defect. So defect exists in any solid material. When we go with their characterization, defects are classified based on their geometry. So here defects are a disrupted region in a volume of a solid. So we have to avoid defects when we manufacture the different products. So what is a defect? Defect, in the defects there are so many types of defects. Vacancy in case of part defects, vacancy, atoms, interstitial atoms, substitutional atoms. When you come to light defect, dislocation happens. Error defects, rain boundary happens. So this is the schematic of point interaction. So here you can see there will be a vacancy, interstitial atom is added. So for that, the substitution atom will be there. So if there is any vacancy, the atom will get substituted. So here you can see where all the interstitial atom are there. If it is not occupied, then it is known as Frankel defect. Where all you can see if the atom has got a vacancy, then that is known as Schottky defect. So line defect happens when dislocation happens when we take A, B, C and D. So another material, if it slides on the surface, and the line AD between the slipped and unslipped portion is the dislocation. So this line AD between slipped and unslipped, which is shown with the pink color here, so there it is the slip which is going to happen. The magnitude and direction of slip produced by dislocation, pink shaded in the is the Burger vector, B is of P of dislocation. So line defect is the edge dislocation and screw dislocation. So here you can see there will be a cubic structure, the atoms will be same. So if there is no atom at the arrangement at the crystal at the center, then you are going to have a edge dislocation. So here edge dislocation happens. So if it is taken into Burger vector, you can see a perfect crystal is there where there is no dislocation of atoms, but in an imperfect crystal there will be a edge dislocation. You can see edge dislocation is there won't be atoms at the with respect to one edge. Here it shows very clearly about the edge dislocation. This is the ideal crystal with the edge dislocation. You can see up to a certain extent atoms will be there, further there won't be any atoms. If you take screw dislocation, the very best example is when we use the rotation system of a dice. Here you can see how the dislocation happens. So there will be a overlapping plane on one another, so it gets displaced to the new position, so there will be a screw dislocation. Here I have shown in the crystal structure also, and also with the dice structure, where you can see there won't be overlapping of the planes with respect to one surface. So if you compare or differentiate between the edge and screw dislocations, here you can see edge dislocation travels faster under load, screw dislocation travels slowly under load. Force required to form edge dislocation is less. In case of screw dislocation, it is more. Atomic bonds around a dislocation line undergo tensile and compressive stresses. Atomic bond around dislocation line undergoes shear distortion. Burger vector B is always perpendicular to the edge dislocation. Burger vector B is always parallel to edge dislocation line. Edge dislocation is represented by perpendicular or capital T. Screw dislocation, it is shown by the clockwise or anti-clockwise screw dislocation. Edge dislocation is line defect. Screw dislocation is also line defect, but the plane of atoms converts into helical surface or screw. So this is the difference between edge and screw dislocation. So what are the surface defects? So under surface defects, you can see there will be grain boundary. there will be a grain boundary. Here you can see the diagram. With respect to the arrangement of atoms, you can see there will be a boundary of the certain lines. So the dark line, it indicates there is a boundary for the atoms which has to be framed. In the optical micrograph of a polycrystalline material, here you can see there will be grain boundary. Grain boundary, it is connected to grain 1, grain 2 and grain 3. Grain boundary, here you can see between grain 1 and grain 2 there will be a grain boundary region. If it is a tilt boundary, here you can see there will be edge dislocation with respect to the atom arrangement. So grain 1 and grain, with respect to grain 1 grain 2 there will be a tilt boundary. So here inverted T is shown, that shows the tilt boundary it is formed. So angle of misalignment will be there when the grain boundaries are formed. Small angle grain boundary it is formed. High angle grain boundary it is formed. Here you can see based on the angle the grain boundary is defined. So twin boundary you can see. So there will be a twin region where the atom gets aligned in the loaded direction. So you can see whenever you add the load on particular atoms, it gets displaced to the new position without disturbing the existing structure. So the region where you are going to mention, that is known as twin region. Further, if you take stacking faults, you can see some of the atoms which are arranged in the sequential order, which is stacked in proper order, it won't be in proper order. So here the difference is observed. Bulk or volume defect will be having porosity inclusion and cracks. These defects are during the manufacturing process for various reasons, and it is harmful for the material in the long run.